So Tom Urim is joining us from Chicago today. He's been a member of the Gateway Development Team for many years now. He's going to talk about some work on the GPSI package, and GPSI stands for Generic Portals for Science Infrastructure. So after being involved in a number of Gateway projects, Tom recognized what Jeff Bezos calls the undifferentiated heavy lifting of Gateway. So there are certain underlying tasks that are common no matter what the the science domain is, and this is Tom's approach that he's used for applying this to a number of Gateway projects he's worked on. Is that an accurate description, Tom?
Yeah, that captures it.
Okay, very good. Thank you very much. Take it away.
Thanks, Nancy. So, as Nancy said, I had worked on a number of gateways before, and in that case, we were building very purpose-built gateways. And I wanted to get around that and have an infrastructure that was easier for the scientists to customize and enabled them to do it instead of them having to hire a gateway developer, for instance, right from the start. So some of these details are captured on this slide in terms of what needs to be done or what we're trying to do. So if we view this typical pattern of introducing some data optionally, introducing some applications, running applications, looking at results, sharing results with your collaborators, this process is very typical, and it obviously there are some aberrations from the process given different science domains with their particular applications and analysis needs. So how can we bootstrap a lot of this but allow for customization to these particular domains to capture these idiosyncratic workflows that happen within particular domains? And then the research questions that we're tackling there are things in terms of how do we effectively schedule jobs? How do we use the user's allocation effectively? What's the best way for us to stage data to the resources and back? And then looking forward, what kind of analysis on the data can we perform on the back end for the user? So the approach that we've been taking is to build on top of Django. Django was used in one TeraGrid portal, the astrophysical modeling portal, and we've used it here too. The reason why we like it is because it's widely used. If you look up Django, you'll find that it's used in a lot of industrial commercial sites, and it has a huge open source community dedicated to it. So it's not something that lives only in our domain, the science domain, or the TeraGrid gateways or Exceed gateways domain. That's a big benefit because it means there's a lot of work going into it that doesn't have anything to do with us. Another thing is that by using Python, we're using a language that's widely used in the scientific community. So where you find scientists and they have to write code to support their own applications, they will very often know something about Python. So if they have to get in here and customize code for GPSI, at least they probably are pretty close to being able to do that. And there are a lot of other reasons to use Django. Its abstraction of database backends is one example. So a lot of things are standardized, and we get that for free also. The Django community has produced apps that can be deployed within a Django instance for many, many things. Like Python, many of the things that you would want to do, you can find modules already exist for doing them. And that means that what we could create is this, on top of the Django web framework, we could contribute one app to this, basically, that would perform the Science Gateway specific functionality that we care about, and it can sit alongside all of these community-developed apps, and that's the only part that we have to work on. So also on the back end, to actually run jobs, we use Swift. This is for describing the workflow and for running jobs, and I'll talk more about that. And then the goal is that with Gypsy, a community should be able to stand up an instance like this. I have said I'd like for it to be as simple as deploying, say, WordPress. So you set this up, and you introduce your the parts that are custom for your domain, and you're pretty much able to get going and get running without any customization, without any without touching any code to make this happen. That's the goal. So there's this overall flow for Gypsy, and like I said, you introduce data, you introduce applications, you can schedule jobs, you view your results. It tracks your results, your jobs and your results, so that you can see a history of campaigns that you've made and the applications that you used. You can see the evolution of your applications over time. You can go back and run individual jobs when you need to reproduce results or iterate from one particular result. And you can download those results and share them on the site. So now I'll just go through the functionality of Gypsy in supporting that flow. So basically, you set up a compute resource. Not all compute resources are, users don't have full control over the compute resources. Right now they're administratively set up. But among the compute resources that have been made available in a particular Gypsy installation, the user can set that up and they say, I need this one, and on that resource, here's my username. And the types of compute resources that Gypsy can talk to is, for now, governed by what Swift supports. So Swift supports file transfer using these various protocols, grid FTP and SSH and HTTP. And for execution, there's a number of different approaches for actually running jobs on the resources. Given this, we've been able to run through Gypsy on a variety of resources from TeraGrid and now Exceed, and on machines here at Argonne, including the compute cluster. We're targeting some of the other ones, although there's an authentication issue that we have to get over. The PADS cluster at the university, so we're bridging to the campus. And third-party resources like those of some of the other people that we're working with to enable their workflows. In terms of credential management, we started out with very basic SSH and public key authentication on the portal, but my proxy is the method that's preferred in this case for gateways to use for obvious reasons. The proxy cert model was a very successful idea and has served gateways very well. So a user can come to Gypsy and establish a credential, and they link it to a particular MyProxy server, and they say, here's my username. And then when Gypsy determines that a proxy cert is required for their actions, running a job, for example, they'll be prompted for their password, and Gypsy will go off and fetch a proxy cert for them from that proxy server, MyProxy server. We've also integrated MyProxy OAuth, which is an effort from out of NCSA and some collaborating institutions, so that we don't actually have to collect the username and password of the user. So you see in this, the flow that you see here is that in authenticating against a credential that you've added to Gypsy means that you're redirected to the MyProxy OAuth service provider, so that you type in your username and password there, and there's a token exchange, and then in Gypsy it can go and fetch the proxy cert, and it has not collected any username or password information. So it's the more preferred solution for handling proxy authentication going forward.
Sorry, this is Nancy. We have a question from the audience about the use of Swift and kind of what goals are achieved by using Swift.
Okay, so I will talk about Swift in a few slides, and so I'd like to
Yep, that's fine.
delay that question for a minute?
Yes.
Okay. So then, once you've set up your compute resources and your credential, then you can introduce your data, and this is done through basic web forms and the way that everybody's familiar with. In this case, what you see is a lot of files from a computational neuroscience project that have been ingested, and you can see they're sizable files. And in that listing on the left, you see a search. This is Ajax-based search, so it fetches these results, and it's actually very responsive. So you can search from among all of the files that are that you've ingested into GPSI, and then on the right you see a view of a single file. In this case, it's an output file from a job that was run. So you see some details of the file, and you can download the file, but you can also preview it. So you get some simple view of the data. You introduce applications, and in this case, defining an application in GPSI means handing it the Swift script, which defines the workflow, and any supporting files, whether they're, say, a Perl script or a Python script or an input data file. All of these things can be bundled into an application definition. And so you see here a list of applications, and from this list, you can run the jobs, you can edit the application. One user can duplicate the application of another. And another thing that we've done here is that that's useful to be able to upload your application code, but to iterate on this, it means that you would be editing the code locally and then uploading it every time. So you can actually edit the supporting files within GPSI directly. Using, again, a standard interface, so we haven't written a web-based editor. Here's some details about Swift, because Swift is used for defining how the applications are actually run and for running them. So there's a simple script here in Swift. Swift uses a C-like syntax, and so what you see here, I'll describe it briefly, is a script that just calls hostname a number of times. In this case, if you look at the for each loop, you'll see it calls it 50 times. And the thing that's happening here is that the Swift app definition block that you see above wraps the executable and makes the call, and then redirects the standard out from the call back to this file, which is the return value from this app. And what that app represents is a job that's submitted. So in this case, this for each, because these calls to the do hostname app are independent in terms of their data, they'll actually be submitted concurrently, subject to throttling configured in Swift. Potentially this could represent 50 individual jobs, so it might show up on 50 different compute nodes, and they would all run simultaneously, and you'd get back the host name from each of them. If you've configured it to run one, then it will submit one job at a time, so again, subject to the throttle. And so this is a very simple way. You can imagine, instead of wrapping host name, you would wrap something else, your scientific application on which you want to run a parameter sweep. You vary the parameters, schedule all of these jobs from within Swift, and Mike Wild, the head of Swift, will tell you that this is a very comfortable paradigm for a lot of scientists who are familiar with scripting, and they really want to carry this concurrency, this control of the concurrency into their scripts. And so that's one of the core tenets of Swift, and that's why he really believes in Swift. What you don't see from this script is what happens when there is a data dependency. So if there were a collective operation after this loop, then the collective operation would block until all of the data dependencies were satisfied. So it would wait for all 50 of these jobs to return, and then it would perform the last job, which would collect all of these outputs and submit another job. So it's actually pretty powerful in terms of handling concurrency within your application. Now, what that means for us, I should stop the person who had the question about Swift. Do you still have a question?
Amit Charazia, did that answer your question?
Yes, it does.
Great, thanks. We got a few more questions have come in, Tom, but I'll save them for the end, so keep going.
Okay, very good. And here you see from the Swift script, so the Swift script can identifies the applications to run, and there can be input parameters to the Swift script. So given that, Gypsy will process a Swift script and determine the input parameters to the Swift script and produce this web form that you see here for running the job. So it has pulled out these parameters and then produces a web form for providing the values for those parameters. In this case, what you see is some combination of default values that were determined from the Swift script and some later curation of this application definition by the user. So the user would say, pardon me, this parameter should instead be named this, you should use this for the default value, and you should collect the parameters in this order. So there is an opportunity for customizing the web form that's used by the user to actually run the application. As I said before, when you're running jobs, it's reliant on a proxy cert on the server side. So if there's an established proxy cert, the user is not prompted for a password, and the job is just run. And on the right, you see a list of jobs that have been run. In this case, there's a lot of details of the particular applications and the owner and the status, this sort of thing. Pardon me. And then selecting one of those particular jobs, you get details of the job. So in that screenshot on the right, you see there are all of the details of the job, the start time, the credential that was used, the compute resource that it ran on. You see some details like queued jobs, active jobs, finished jobs. This updates periodically through the execution of the job. You see parameter values, input files, in this case none, output files, and here you see this section, this application output runtime. So the files are subdivided into different types. And then for the output files are displayed in this, then the lower section, this output section. In this case, we have this job produced a lot of PNG images, and they're trivial content for the web browser, obviously, so they're just splatted on the page. If there were an alternate representation of this, then the user could choose to view the alternate representation. Another example is in working with, say, molecular models. You might output PNGs, but you also might use an embedded JMOL applet for viewing the 3D model so that you can interact with it. And that control over how things are represented and which things are represented lies with the person who creates the application. So that person can say, this app should display only this subset of the output files and provide an XSLT transform for controlling how those files are represented. And it could be that they wrap them so that the user can select between, again, say, the PNG and the JMOL representation. Right now in Gypsy, there aren't really formal controls for sharing data among users, jobs, and applications. So we're defaulting to things being mostly open. So if you want to do your work and have other people not see it, then you probably want your own instance of Gypsy. Where that should go is that we have control some role-based access so that we have control over letting your collaborators see your work, but maybe not your competitors who are on the same site. Here's just a short bit about provenance, and you see I highlighted the P in provenance. It's provenance with a small p because we're not actively doing research in this area, but we GPSI does capture details which make it really convenient to see where your campaign has gone, what you have done, which values you specified, the results that were produced, and then being able to carry those into another execution. So if as you run jobs and you see some promising trend in the past, for example, you could go back to it and pull off branch from that one and run jobs from that one using that application code. And it's a much greater convenience than it is a difficulty to support. We really get that very easily. So lest I give the impression that GPSI is a production ready-to-go framework being used for a lot of things, what it really is something that's just getting its legs, and it has some issues, but we're trying to use it in a couple of domains, one of them being a smart grid project that we have here, in which you see in the top right image, we have jobs that execute against actually some proprietary code that's installed on only a particular cluster or two clusters here, and produces these images by analyzing electrical power usage over thousands of hours using data from Illinois. So you see in this case, each of these images is at a different time. Beyond this, what we've done in this case is to take this progression, all of these time steps, and then use a separate GPSI application for animating them. So it's really just a call to, say, FFmpeg for stacking the frames and producing an animation so that you can see the change in the electrical usage over time. The lower image is a very early example from work with materials folks here. They have this pile of data, molecular models that they have worked with in the past, and because of the way that they've computed them, and we find this is typical with a lot of different groups, they have, one scientist will have his data spread across 4 different compute resources representing different periods of time when he was computing, or different types of analyses, different availability of machines. So he has all of this data spread across these different resources. And when you consider him working in a collaboration with 3 or 10 other people, now the problem is compounded yet further. So they have all of these models, and they need to be able to categorize them and collaborate on them. And what we're working on is to allow them to say, for each file, we'll extract this metadata, we'll push this into GPSI with the metadata, and now the metadata is searchable using this integrated triple store. So they can search for files that meet certain criteria, and then see again this application prescribed representation of the data within GPSI. As I said, this is still early work. So, and what we're looking at for the future is to do more analysis within GPSI. I mean, the data is all there, and in a lot of cases, the data is non-trivial to transfer. And so, what we really want to do is further analysis on the compute resource and look at different representations of the data. We've talked about dynamic provisioning of applications. So an application might not have an explicit stack of files. It might instead point at a Subversion or a Git repository. And as needed, the user could say, pull a new copy from the repository and build it on this particular compute resource so that it's available for this application to use. There's obviously, I don't think I have to enumerate the hurdles in doing that or getting people to accept that model, but it's a very useful model for our users. I sit one floor below the Globus Online guys. I talk to them all the time, and yes, it seems like an obvious target for us to consider integrating as one of the file transfer mechanisms. Mike Wild, again, the head of Swift, sits upstairs with the Globus Online guys, so he's talking to them regularly about enabling Globus Online within Swift directly. And then in one of our past efforts, we had done work to look at how can we catalog all of the user's data across various compute resources that they use. Again, this goes to the problem I mentioned with the materials guys. If you can discover all of your files across all of the resources and use them as inputs within gypsy workflows, it's a terrible convenience for the user, and it allows us some opportunities for optimizing where jobs run based on data locality, for example, and simplifying that from the standpoint of the user. In closing, I mean, I put up the acknowledgements slide, but in closing, I'd like to say, again, the goal here is not some, the pinnacle of technical achievement, but it's convenience for the user. I think that really the scientists should be able to carry the applications that they know how to run into an environment like this and get started very quickly. So that's sort of the driving use case for us. And with that, I'll close.
Tom, thank you very much. We have a few questions that have come in. I was interested to see that you're using Django. I've heard from several gateway developers over the years how easy it is to get started with that. So I think that's a nice approach. So someone asks, does Gypsy make use of community accounts?
It is not now, but I have routinely felt like it should be. It's a convenient place for us to sit right now because we're not really pushing into production, but it definitely should. We'd use a community account with SIDGrid, for example, and so it's an obvious target here too. And in that case, where now we pretty much let users define what they run and do whatever they want, and even browse files on the remote site, some of those things would clearly need to be constrained if we're using a community account. Right.
Yeah, I know that some of your gateways are set up for individual allocations, and SIDGrid, like you mentioned, uses community accounts, and then there's different accounting things that you need to take into account for community accounts.
Right, exactly.
Yeah, very good. Let's see, someone else asked about a URL to download Gypsy. It sounds like you said it wasn't a production tool yet. Perhaps they could follow up with you offline. I'm not sure if you have a URL for it.
I don't even have a URL yet. It's something that we've been only talking with people about casually. I'd be happy to talk to whoever it was or to anybody else. The most promising comment I can make is that I'd really like for it to be, like I said, something that's as available and easy to deploy as, say, WordPress.
And Ralph Roski's had a question?
Yeah, I just wondered what else was comparable that might be available. I mean, I'm just trying to understand. This is your view of this, but are you the first person to try this sort of thing, or are there other ones and you didn't like what they did, or what's the story?
Well, I really think that in this particular instance, I benefit from the fact that, like I said, there's such a widespread Django community that provides so much, and all I have to care about is the one app, Gypsy, that I need for Science Gateway's work. It's very much the model that's been used in gateways for a long time in the Java world, where you have, for example, the JSR 168 and other specifications which seek to say, look, I have this portal environment and I want people to be able to write pluggable code so that they can leverage, so that we create this repository of applications that people can just pick up and use, that's a great model. And so in this case, the same thing has been done in the Django world, except it's according to a Django specification instead of a Java specification, right? So if it were done at the language level, then that would be great, right? But what we have instead is that you could do the same thing with Django. So I know I'm not the first one to do this. JSR 168 dates back a number of years and has proven successful in a lot of different Tergrid Exceed gateways. One of the, as I mentioned, one of the advantages I think we have in this case is the fact that we're more likely to find Python programmers than Java programmers among scientific teams. And so
that's the sort of answer I was looking for. Thank you.
I was just going to add, as much as my goal is to have the scientists not have to write code at all, in this case at least if they have to, then they're likely to have some handle on Python and they can move ahead with it.
Got it.
Yeah, we do see in the Gateway program kind of very much a matchmaking between the skills of the end users. Now, some are quite familiar with Java, but I think Tom raises some excellent points here with his approach. Let's see, we're a tiny bit over time here. Any other questions from the audience for Tom? Tom, thanks for a very nice talk, very interesting work. Thank you for taking the time to work up the slides for all of us. And DJ, too, if you're still on, thank you very much.
Thanks for the opportunity, Nancy.
Yep, we'll talk to everyone again, hopefully next month. Thank you again. Bye.
Thanks.